Ladies and gentlemen, thank you for joining today. This is your host Nino, inviting you to a very geeky episode concerning the Spectrum modern-made retro computer by Retro Games, having a name not so unlike the La Trattoria of Mickey Blue Eyes, which in today's episode, though, we shall be turning into a sort of late 1940s mainframe / supercomputer, whatever you call it. You will be able to compute with American quadrillions or European billiards, anyway, 10 to the 15th, and not only with whole numbers, but we will also be dealing with a fractional part going behind, working all with precision, for it is not floating point configuration, but a fixed point configuration. But let me tell you maybe how this is all going to be possible. So I have on this bird head, which constitutes a USB stick, a port of a programming language which I created called Evo in honor of my beloved dad who passed away a couple of years ago, in the version Tsvetanka 4, named after my mom. And this programming language is geared towards permitting even lowest power devices, lowest resources devices to be used as full computational facilities in a very CISC style, like complex instruction set computer, where you are having few instructions and few memory positions, in this case slightly over 200 each, but each instruction is allowing very complex operations, and there are enough of them, including such which work on number ranges and so on and so forth, so that you do not need to write many instructions but can compute a lot of things in most confined spaces. And today I want to show you how that looks. So here, with the Spectrum being turned to classic mode, let me just press this home button, or what it's called, and then let's go for media select, and there it recognizes my USB stick, and there is already the Evo C4 port, so Evo Tsvetanka 4. I'm going to say M to select it and enter to launch it. And here we are at the prompt of zeros. Now, one speciality about Evo is, in particular in this extremely primitive incarnation, that it works here solely with numbers. There is no other character you are using, and in fact, there is no display of anything but numbers. In particular, negative numbers are just such which on the leftmost position are having a 1. So what do these numbers look like? What does this all look like in practice? Let me demonstrate to you. So there are certain 4-position instructions which we can give, which here, as we are in the interactive mode, can serve to set up the system and explore it. And for instance, 2222 means show me a number and a couple following here. 5 numbers, because normally when a person wants to check out a number in a program, you are interested also in the next couple ones. From which address? Let's say address 1. Entering that, and it is showing you zeros, because yeah, that's what we are having. Now, for visual support, I have permitted myself to separate the integer part, yes, exactly these 16 positions here, from the fractional part by a space. So maybe that's the only thing where I print something that's not a number. That and the carriage return. But you see that even on highly restricted displays, which would not be able to show anything but numbers, you could use such a system. You could even glue just a line to your screen separating them if you can't print the space, just so you don't have to remember or count numbers. Okay, so seeing these numbers, what would, for instance, a number 1 look like? Can we enter a number 1 somewhere? Entering a number is happening with the command 4444. Where shall we enter it? In address 1. And this is an important thing. You're not having here variable names, but you're dealing with addresses. Whatever you're programming, you're directly saying which address it shall have. Okay, now it is asking us to enter the number. Let us enter -1. So that would be entered in blocks of 4 numbers each. So the first block will be 1000 in order to have the most significant digit as a 1, which means minus. The rest is just a numeric expression, but the leftmost one is for the sign. 0 for plus, 1 for minus. Okay, got it. Next block of numbers will be 0. I can also enter just 1, 0. It will take it for the 4 positions anyway. Next portion will be again 0. And the final portion will be a 1, because we want to enter -1, right? And then for the decimal part, I will enter again 0 and 0. So that is what -1 looks like in the address space of Evo. And if I say again, I want to have that displayed from the first number on, then you see it prints it just in its regularly visible form. And if you would like to enter instructions, you do that in a way not so unlike with BASIC. It's just the instruction format is fixed. You always enter 5 numbers. The first number is the address. Where would you like something to be in instruction memory? Then you are saying what instruction shall be used. That again is a number. Then you're saying which first, which second, and which third data addresses will be used in that instruction. Commonly, the computation is happening between the value at the first data address and the value at the second data address, storing the result at the third data address. Now, to just give you a flavor of what that could look like, the instruction position 0 means immediate execution. It is not then going to go anywhere further. It's just like calculator style, doing a thing and then returning. Okay, so instruction number 0. The operation we will be using is 9, which is plus. And the first datum we shall be working on is the one at data address 1. The second one shall be again the datum at data address 1. And the third shall be the datum at data address 4. Just to distinguish the addresses from the contents. It now tells us that it has accepted the instruction. This is the first line. And the second line is a brief execution trace telling us, when it is executing, it is displaying by default the operation it is presently conducting to allow you a little bit to trace things along. So this was also a trace. And now if we look at our memory and say from where? From 1. Then ta-da, -1 plus -1 gives -2. I will show you a more complex example later on, but I just want you to get the hang of it, that we are operating here really on something purely with numbers, really just the top row here and the enter sign. We do not enter any minuses, we do not enter any decimal points and so on and so forth, yet we can compute, pretty impressive numbers if we wanted to. Now, it should be mentioned that this is like Harvard architecture. The instruction space and the data space are fully separate. So I can have an instruction in position 1 and I can have a datum in position 1, and there is no conflict between that. There are certain instructions which allow indirect addressing, even such beauties like computed goto and abominations, which in every textbook are written, do not do that. They're all allowed here. But it is actually quite powerful language if you would like to get into it. And perhaps now that you see how we can enter instructions and display data, I can enter a little program just for the demonstration purpose of how this could be used. You see also the similarity here, a little bit too basic, if you will, insofar as you just enter things with their addresses and you're not even confined to enter the instructions sequentially, as long as you just simply say which instruction you're entering now, similar to the lines in BASIC. And now our program shall be one which is taking two numbers, the cathets of a triangle, and computing the length of the hypotenuses. The instructions I shall comment, though you may of course have a look at the link in the description, which I will hopefully not forget, where you can find the actual source code of this. And there you can see what sorts of operations are possible. They are all mentioned there. Also the ranged ones and so on and so forth. So trust me, dude, this is sort of documented, but mainly for the interested programmer. I mean, there is a documentation for a previous version of Evo, which is insofar different as it operates only with two addresses, and the result is stored in the first. This is different insofar as we're having three addresses, and the first and the second store the result in the third. So it's not overwriting everything. It looks a bit like a virtual machine, and you're not wrong with that. If you were to say, hey, but this is a bit like it, that's indeed the case. So let's start with instruction position 20, just like that. I mean, I can just want to do that way. And then we shall multiply, which is instruction 11, our first value, or first cathete value, which will be in data address 7 by itself. So again, data address 7. And please store the result on the data address 12. You see, this time it did not execute it immediately because it is not a 0th instruction. It is just one line confirming what you have just input. In case you're curious what your program looks like, you can always use the command 1111 and tell what you would like to look at, and it is going to be but this is of course under 20. It is going to be showing you the instruction memory in this place. So you will see it has taken our instruction. Okay, 21, same with the other cathete, right? So instruction number 21 shall be a multiplication. The other number shall be in position 8 and multiply it by itself. Store the result, please, under 13. So the square of the first one is in 12, the square of the second one is in 13. Next, we shall add these, right? So instruction number 22 shall say add, which is operation 9, the number under address 12 to the number under address 13, and store the result under address 14. Data address 14. Taken. Now, if I wanted to, I could enter an instruction out of order. I shall do so. Instruction 25. And instruction 25 will be a jump instruction in order to not wait for it to go through the entire memory, whereby instructions of 0 are just like no operation, it just ignores these. And we shall say jump. The second address will be, the first address will be ignored. To position 219, that's the last instruction. In other words, once it exhausts execution memory, so it has gone through the entire memory, it has reached address 219 and wants to go beyond, it stops executing. So that means just stop immediately to do whatever you were doing. And 6 means make the jump unconditional. We normally would be checking the first datum address for greater than, equal, not equal, and whatever to make a conditional jump, but we just want an unconditional one. Get out of here. Okay. And let's enter an instruction 23, whereby we will be using operation 32, which is a square root. So compute the square root, please. But it is a ranged square root command. So it is ready to compute the square root of an entire range of numbers. Our range shall be 14 and 14. So the same number, the range limits are inclusive. So just one number, please. And store the result, so the hypotenusis length, under datum address 15. If we now were to look again at our instruction number 20, you see it has accepted here already a couple of things. Now, you may certainly note that we did not actually enter anything for instruction 24. Well, that's just simply going to be an instruction full of zeros. So let's look at 23 and 3 and following. 23. You see, this is the same 32 as here, so it's repeating. Then comes the 000 instruction. That will not interfere with our computation. In particular, it will not cancel it or crash or anything uncomfortable. Evo is really trying not to fail. This is visible in many places, including by the fact that the division by 0 simply gives you 0 and not an error. Yeah, some people will protest. I love to revel in your schemes. And having that then is a jump instruction to terminate the program. Let's trigger it. How do we start it? By an immediate instruction. However, when the immediate instruction is a jump, it does not return. But before we start it, it would of course be sensible that we enter some values, right? So let's say 4444 to enter. I'm going to use the classical values of 8 and 6 because that gives you a hypotenusis of 10. And under number 7, so address position 7, let's enter now our 6. I can press 000, you know, in order to create the guiding position of the number. Okay, taken. If I were lazy, I can just say 0. We'll take it as well. If I'm even lazier, I can just press enter. It will take it. I can then say 6 because that's what I want to have really. So this is the integer part. The first 4 numbers express the integer part, just the leftmost digit is for the sign. There will be no fractional part. And it has accepted the number 6 under position 7. Now under position 8, let us give it the number 8. Yeah, so position and number here are the same. Taken. And now let's launch the whole affair by saying instruction number 0, a jump please, and it will be irrelevant what this datum is because it is going to be an unconditional jump, to address 20, the first address of our program, which will run to address 25 and then just jump to the end of instruction space and thus terminate, and make the whole thing unconditional. And now watch, it will show you the tracing, and in particular instruction number 23, the square root is going to take a long time. So you see now it's waiting, it's computing. It's not crashing, it just needs a good while. Ta-da, did it. Okay, and you see how it jumped 219 and then it executed the no operation there, and that's it. It returned us to the prompt. Let's look at our results really like in the 1940s or 50s. We're just looking into memory in order to see your results. So we're pressing 2222. Where shall we have a look at? Let's pick instruction, not instruction, but data position 12. I think from there we should see everything interesting. And we do see it. So here is the 6 squared, the 8 squared, the 100 from the addition, and the 10 from the square root. And that way, ladies and gentlemen, you are able to do some pretty serious computation, if you wanted to, on a ZX Spectrum or the Spectrum replica of it. But you know, it's a tape file, so for the lovers of classical machines, you may try to run it on the original. I shall prefer to run it on this emulator. But all the same, that way, with a little bit of effort, you can turn the Spectrum into a serious machine. Well, whoever of you wants to design aircraft on that or explore the advantages and fruits of nuclear fission, I don't know, and I wish you much success in such endeavors. From me, that's it for today. I hope you enjoyed this episode, and I am inviting you to come again and enjoy further adventures. If not subscribers yet, it would be very kind of you to consider joining our friendly club. Until we meet again, I wish you a wonderful time. Thank you for watching, and from me, goodbye. Post dictum. Here you see the GitHub repository where all sorts of versions of Evo are stored. We will explore this topic in great detail in the future once this channel has grown a little more. Just for the present moment, I wanted to let you have a glimpse into days of the future past so that you may enjoy it on the Spectrum.